With Meghan Kane talking about bootstrapping the machine learning training process. Give it up.
Hey everyone, thanks for coming to my talk today. Today we'll be talking about bootstrapping the machine learning training process. So if you've been curious about how to do something custom with machine learning for iOS apps, we will review the end-to-end process of doing it. We'll go from defining the problem and gathering the data through the training a custom machine learning model that will be compatible with Core ML. So yeah, as I said, I'm Megan, that's my Twitter handle, and I'm an iOS developer at Novoda. It's an app consultancy, and I work in the Berlin office. So we're going to focus on training, but I'm just going to do like a overview so that everybody's on the same page. So when Core ML was introduced at WWDC 2017 for iOS 11, there was a wave of excitement propagating through the community, perhaps too much excitement. And the Core ML APIs introduced in iOS 11 enabled seamless integration of a pre-trained machine learning model into your apps to make predictions on the device. So a model that's in an ML model format that Apple came up with could be easily dropped into a Xcode project, automatically generating a Swift file for you to work with directly. And the Core ML framework APIs are very simple and succinct to use, and this vastly improved the options offered previously with Metal and Accelerate. There was and still is a lot of hype. So since there was a lot of hype, for the rest of this talk, I'm going to refer to before Core ML was announced as BC, before Core ML, and after Core ML was announced as AD, after Dub 2017. So before Core ML, you could still put a pre-trained machine learning model into your app to make predictions. However, there was a lot of heavy lifting involved. So you could either use Accelerate and BNNS, which targeted running the prediction on the CPU, or you could use Metal performance shaders. Metal performance shaders, convolutional neural networks, like a mouthful, and this targeted the GPU. Yeah, this is a lot of work and kind of specialized knowledge, so very few people were doing it. So at WWDC last year, Core ML was released, and this drastically reduced the workload for us. And Core ML abstracts Accelerate or Metal away from us, and it decides whether to use the CPU or the GPU for us, and it just exposes very simple APIs for us. So yeah, the crowd cheered and the community was overcome with excitement, blah, 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 for what the future holds for machine learning for iOS apps. So is it all the hype? It's definitely a powerful tool. Machine learning is a powerful tool in general. However, it's still just another tool, and we have many tools at our disposal to solve problems in our apps. So beware of the golden hammer rule. Providing a valuable user experience in our app that solves the problems we set out to solve is the #1 priority. Not necessarily just using the newest shiny framework. So bearing that in mind, it's just one of the tools we have. How can we think about machine learning as iOS developers? Well, not to be too negative, but just to be practical. First, we should ask ourselves, can this be solved without machine learning? And if so, you should probably choose that because it's a lot easier and less overhead in general. So let's just take a very general look at machine learning type problems versus not machine learning type problems. This is definitely not exhaustive, but just for a reference point. So if we define the basic unit of solving a problem as a function or a model in machine learning speak, machine learning takes the approach of solving a problem by enabling a machine to learn a function on its own. You don't tell it what to do explicitly. So an example of this, which we're actually going to use for training a custom model in this talk, is classifying sign language alphabet images. So say you wanted to do this in real time with your app. On the other hand, the traditional non-machine learning approach that's been around forever is to just explicitly define the function. There are tons of examples of this, but just a really simple one would be determining if a number is even or odd. You would certainly not want to use machine learning for this. It may actually perform worse with machine learning. And it's a very, very simple algorithm. So if you decide to use machine learning, still go with the simplest solution. It's kind of like a theme. So the next question I think we should ask ourselves is, why would you want to do machine learning predictions on the mobile device? So the other route is making a request to a server, and then the server would like host the model for you, and you would be fetching the prediction that's made server-side. So why would you do it on the mobile device instead? So the first and strongest argument is that it's quite time-consuming and expensive to send data from the device to the server across the network. And this will especially be cumbersome if you're trying to do something like real-time image or audio classification. And we are going to be doing those in this talk too, so there are plenty of examples. So on-device prediction yields a low latency user experience. Secondly, the data passed into the machine learning model is kept locally, so it's in the interest of user privacy, and this is a very relevant concern right now. So if you decide to do machine learning predictions on the device, first check what's available from Apple. So probably a lot of you have seen this already. I just want to put everybody on the same page. Apple provides us with 6 or 7 out-of-the-box machine learning models that are already in the ML model format. And the 2 types of models that they provide for us are image classification of 1,000 common categories. So it will classify images into categories such as trees, animals, food, vehicles, or people. So there are a bunch of options for these, and they vary in a lot of the different machine learning type parameters. And I ordered them from the size that they are. And so I think the ones that are suitable to use, if this solves your problem, would be to use SqueezeNet or MobileNet. Just because they're smaller doesn't necessarily mean that they're worse at making predictions. A lot of them were just released by academia later on in the machine learning evolution process, and just are doing things smarter and more compactly. And MobileNet specifically is an industry standard to use, so you can certainly entrust in that. The other type of model that's available from Apple, the task that it does, is scene classification of 205 categories. So this will not just classify the specific object, this will look at the scene overall. So it can detect airport, terminal, bedroom, forest, coast. This is 25 megabytes. So this is also something reasonable to use in a mobile app. So if these don't suit your needs, which they probably won't actually if you want to do something custom, you're going to have to train a custom machine learning model. So we're going to focus on this part. So for this, there are 2 steps involved, and we'll go through step 1 in the most detail. So the first step is to use a framework for training. So if you have looked at any of these before or read any tutorials, you might notice that there might be a different example for every single blog post, and so it can seem kind of overwhelming. But I want you to not quit there, because that's basically just because machine learning is still in the early stages, and we still haven't settled on a gold standard. And we may not ever. It might be good to have some variety. So some frameworks that are common to use are TensorFlow by Google, Keras, Turi Create, which is released by Apple and is actually open source too, and Caffe. And we're going to use TensorFlow for this talk. TensorFlow, and actually all of these are in Python, so we're going to have to stick with Python for this talk, so sorry about that. But TensorFlow is going to be offered in Swift, hopefully very soon. It was announced in March at the TensorFlow Dev Summit by Chris Lattner. So once you have used one of these frameworks for training, you have to convert it to the core or ML model format. Sorry for the typo. So to do this, Apple provides us with core ML tools, which will take some custom machine learning models from specific frameworks and convert them into ML model format. And there are also other open source solutions that are available if that one doesn't work for you. So there's a TensorFlow core ML converter that was offered outside of Apple. So yeah, just the rough flow. So you would train in one of these frameworks that's on the left, and there are actually even more available. And then you would use core ML tools or one of the open source solutions for converting the model, and then you would have the ML model format, which you can just drag into your Xcode project. So in many ways, in general, it's been quite a year. Some good stuff, some bad stuff, but it's definitely been a smash hit for releasing or making major changes for machine learning training frameworks. Like as I mentioned, there are so many of them. So being overwhelmed by this is definitely very common. So yeah, Core ML was released. That's not a machine learning training framework. The ones that are in yellow. There was like Michelangelo that was announced by Uber. There's Theory Create was open source by Apple. TensorFlow Swift was announced in March. Theano was one that was deprecated. So it's kind of like all over the place. So like TensorFlow, I think, is one you can stick with, though, for now, because it seems like they have a lot of plans for the future. I even made one myself. It never saw the light of day, because, and also it was just like a pet project for me to learn. And it had a lot of compiler crashes because I was trying to use the Python Objective-C bindings from Swift. But that's the extent that it went to. Like, that's how many frameworks there were. So raise your hand if you've looked up how to train a machine learning model and have come across a cat-dog image classifier. OK, keep your hand up if you are making an app where you would want to classify a cat or a dog. I don't think there's like anybody. So that like begs some questions, like what can we do that's like a little bit more practical? So these are like the guiding questions for the rest of the talk. Like, is machine learning practical for my app's use cases? Are there barriers to entry? Maybe some people have read or heard about like data, computing power, having a PhD in machine learning, or time could be barriers, or so-called barriers. Which framework to use, and how to navigate all the material out there. So is it practical for your app? So these are just some examples that would, like tasks that would be more suitable for using like machine learning. So image classification is the most popular one, but let's try to move beyond that even. So audio classification is also something that is very relevant for ML. Speech recognition, text classification, object localization, gesture recognition, optical character recognition, and translations. So it doesn't have to be like your whole app that solves this problem. It could just be like one part of your app or a feature. It could be a great candidate for utilizing machine learning. So we want people to go through all of these like types of tasks, but I think it's important to like go through them because I think it's a good way to like embrace idea like generation for areas where you could use it, and also to like remember that it's fun to experiment with these things. So even if you do it for like Hack Week project or like in your spare time or something, it could be fun and like lead to something further down the road. So yeah, as I said before, you can just like use this for a feature. Yeah, so I think this like kind of goes like along with like one of John's points yesterday about making sure that if you want to do something, you like keep the scope pretty small so you can like stay focused, because that like gives you more of a chance to actually like reach that goal and then like have further motivation for the future. So there will be some trade-offs for doing this for mobile. Just keep these in mind. The size of the model, the time it takes to run predictions, and the supported layers like in the deep network. So these, besides the third one, I don't know, like these in general are just mobile-specific concerns, just like fit to machine learning. So it's just something that you probably have in mind in like a general sense for other problems that you're solving. So with all of that like upfront background information, what's the training process and how do you bootstrap it? That's what we're supposed to be talking about. No, we're not going to do it like that. Maybe some people have come across tutorials on the internet that seem like this, that like you just have a small setup and then all of a sudden you're like doing something revolutionary in machine learning. Hopefully like we'll stay away from this, and hopefully people can not think that it's so opaque. So I think that the end-to-end process can be defined in these like 6 steps. So we're going to focus on steps 1 to 3 because 4 to 6 are covered in like a lot of really great talks, WWDC and community organized talks, blog posts. There are even like 2 other talks about machine learning at this conference like later today. And I also have a Udacity course that's like pinned to my Twitter page for step 4 to 6. So yeah, the first step would be define the problem. We've gone through some of that, and then you want to gather the data, and then you want to train the machine learning model. OK, so let's go through some examples. So let's say we want to we have a problem that can be like described as like wanting to classify American Sign Language alphabet characters, and you want to do it in real time. So you want to do it on device. So that's our problem. And then you have to gather the data. So this is where you might be thinking, like, I don't have millions of annotated images of individuals signing the American Sign Language alphabet for each character. What do I do? And also, maybe you read that these are barriers to entry, like a large data set, access to high-end compute power, all these like crazy GPUs and TPUs, a PhD in machine learning, which has really only been around for like not very long at all, or all the time in the world. But luckily, these are not barriers, and if you have these in mind, then like you can hopefully like set them aside. So one of the main reasons why you don't have to see these as barriers is because of this really cool technique that we're going to focus on called transfer learning. So yeah, it's time to bring transfer learning on the scene because it alleviates all these barriers. And so in a nutshell, we can use transfer learning to use the knowledge that was distilled or learned from a source task, such as recognizing 1,000 different types of general images in MobileNet. And we can use that knowledge that was learned to train a target task, such as our American Sign Language classifier. So you can think of it as like sort of piggybacking off of work that you already did, so that you don't have to do everything from scratch every single time you want to make a machine learning model. So I don't want to like start saying vocabulary that might be confusing. So deep learning is just a neural network model with many layers. So like deep means many layers. And they have deep neural network. There's a really good reference by Heartbeat. It's a blog by like a machine learning company that's focused on mobile, and they have a glossary with like a lot of machine learning terms that are relevant for mobile. So I highly recommend checking that out. Okay, so back in BC, way back, people used to train deep neural networks from scratch. And now we can stand on the shoulders of giants' work, like such as like Google, all of the big companies, and anyone from the community who's put out work, and academia. And we can utilize transfer learning for our custom task. So in a nutshell, like don't reinvent the wheel. So training from scratch would mean that you would, this is a deep neural network visualization. It's very like kind of like rough, like from the very high level. But so like, as a reminder, you would have, to the computer, the input would be this image. If you're trying to classify a car, this is like a really nice visualization I found online, so it's not specific to our task, but it would be the same for the American Sign Language task. So to the computer, the input image is just a matrix of pixel values. And this matrix is a tensor. So that's where like TensorFlow comes in, like that whole tensor concept. And each of these layers just corresponds to a transformation on your input, until finally the output tells you the probability distribution of what the image is. So they left out the probability distribution, but it would have like, it would probably have something like Audi A7 would be like, it would be 98% sure, and then it would have like maybe 1% chance that it was some BMW, and they would add to 100. So for our sign language classifier, this would output what letter or character it thinks the image was with the corresponding probabilities. Yeah, so the layers closest to the input, you can see on the top. This is like a visualization of like roughly what the neural network sees. You can see that it's detecting very general features. So each of these layers is like a feature detector of like what it can see in the image. So you can see that it detects like an edge or a gradient. So the image that's right next to the car. And then in the middle layers, it's detecting like a little bit higher features like corners and grids and like maybe some wheels I see. And then towards the output layers, that's when it's starting to, the neural network starting to understand like what a car actually is. And in our case, what like a specific sign language character would be. So it intuitively makes sense that you should be able to reuse some of these layers from like a source task into your target task. And you should just have to train the last couple of layers, which can save you a ton of work, like in computation power needed, and also like the data that's needed. Because the reason why you need so much data when you're training from scratch is because you have to train for the entire network. So you're trying to teach the network how to recognize everything from very basic features like edges to the specific thing that you're trying to classify. So yeah, that's transfer learning. It's a little bit hard to see, but yeah, basically this is just a visualization of what I was just saying, where you can just use the source task, and then you can transfer some of the parameters from that model into a target task, and then just train the last couple of layers. So why transfer learning works is like something that actually has like mathematical foundation. We won't go into too much detail, but the gist of it is that like neural networks and like deep networks are universal approximators. So in theory, they can approximate any function, which is like a pretty powerful statement, actually. So that doesn't necessarily mean that using a neural network is the best route to go, but in theory, if you had like enough resources, you could model any function. So using transfer learning, like you're starting off with parameters from a different task, and so even though you're like starting with something different, you'll eventually be able to approximate your custom function because this is like a mathematical underpinning of neural networks. So gathering the data for our American Sign Language task. So how much data do you need? It depends on the problem, but usually you just need like a couple hundred images per category when you're leveraging transfer learning. And where can you get it? If you don't have it available at your company or like on your like personal database. So you can just Google for data, and you'd be surprised with how many open data sets there are. A source that has like a ton of data sets that are usually pretty clean to work with too is Kaggle, and I highly recommend checking that out because they have very good documentation, and they also have challenges you can do to train machine learning models. So it's a good like guiding source. You can also record video for like images and use FFmpeg to take the frames out. That's kind of like a hack, but it works. So yeah, this is Kaggle. As you can see, they have like over 6,000 data sets available. So if you don't have enough data, you can also like take a small amount of data and augment it. You can do like transformations on the data, like cropping, rotating, shearing, warping. We don't have time for this either. There's a lot of material, but you can check out this really good video by Andrew Ng, who's like a deep learning, machine learning like expert. And this goes through how to do data augmentation in like just maybe 10 minutes. Yeah, so I found the sign language data set just on the internet. I just Googled for it, and I like checked that it was like a pretty representative sample, and then I also checked that it was like in the correct format that TensorFlow would want. Sometimes you have to do a little bit of pre-processing. So this data set had 3,000 images per alphabet character or class. You don't actually need that many, but yeah, just wanted to like say that up front because it does affect how the model trains. So after this, we're ready to train our model. And so we have a like very handy TensorFlow script that was made available by Google that we can use to use transfer learning to train this. So yeah, training the model. So the tutorial that I like the best from Google, they have tons, but it's called TensorFlow for Poets. It's just like really, really nice how they do it. Like they have like 8 steps, and everything is explained like very nicely and succinctly, and then they like have inline coding, and they tell you like what GitHub repository to use and what's happening at each step. So since this is readily available and a lot of people use it, and so there's a lot of like Stack Overflow posts about it too if you run into issues, it's a really easy place to start. So I highly recommend doing this if you do this after this talk. So yeah, confession, this is in Python. I guess I already gave that away, but yeah, it's not Swift yet. So since this is in Python, if you don't want to mess around with your system installation, I recommend using virtualenv or something similar to that. So you create a virtual environment, you can name it whatever, and then you activate that environment. And then you have to install whatever dependencies are necessary using pip, which is like the Python package manager. So for this, we need NumPy, 6, and TensorFlow. If you don't install them, it just tells you to install them, like when you try to run the training script. Yeah, so you have to copy the data set into like the TensorFlow like repository, and in the TF files folder, it's actually like specific where it needs to be because that's where it's going to look, unless you want to modify the like transfer learning training script. And then after that, you can start TensorBoard in the background if you want to like look at monitoring how the training is doing. It's a really, really useful resource. You can see like how it's improving over time. And yeah, it's like very robust. Then you just set some environment variables and the image size and the architecture. And then you just run the training script. This is in the TensorFlow for Poets tutorial. And it like tells you what everything is, but like we're kind of short on time, but roughly, basically, you just give it the name of the script, and then you give it the bottleneck directory. The tutorial goes into it a little bit more in depth. How many training steps? So this determines like how long you're going to train this for. So 500 is like a good starting point. If it doesn't do well, then you can increase it. It's just going to take longer time. And then you have the model directory. where the model's going to go, and then summaries of it. You have like output graph, output labels, architecture, image. These aren't like super important to like know like the minutia of. You can actually just keep everything as default except for the steps, architecture, which you define in an n variable, and where your data is. So how did the training go when I ran this? So it only took 20 minutes to run on my MacBook from using transfer learning on the image recognition of a generalized model that has 1,000 general categories to our American Sign Language alphabet classifier. And in those 20 minutes, we have 95.3% accuracy on the test data. So you can see like how powerful this transfer learning technique is. So yeah, it like prints it out for you when it's done. It has a lot of like debug output too. So yeah, I have like a pretty standard MacBook, like I guess sort of powerful, but just to give you like the scale of things, because it would take longer if you have a less powerful MacBook. But yeah, I have like an i7 and 16 gigabits of memory. Okay, so I'll try to go through this really quickly, but just to give you like another idea, you can do audio classification too, and so we'll go through this example of if we define a problem as an audio classifier of urban sounds, because there's a really nice open data source for this, we can classify a sound that comes in as like they have like an air conditioner, a car horn, children playing, drilling, siren, a couple of more. So yeah, this is already readily available and very well documented by NYU. So the link is here. And I'll send the slides out after. So should we use raw audio? You can, but it's very computationally expensive. And so we can do a little trick in pre-processing in order to have this more similar to our last example. So the way we can do this is we can take a trick from like auditory research, and we can translate the audio wave file to the image representation as a spectrogram. So yeah, if you do this, and I just had like a script for this that I can also like push to GitHub after this, then we change our wave file into 3 dimensions, which is like the time dimension. It's just like the waveform, as you would recognize that. So time and the x-axis, frequency and the y-axis, and then the loudness of sound intensity is the color. So yeah, I just wanted to show you like how this was structured, very similarly to the last time. But there's a conversion script that I have. Yeah, so once I converted it, this is what a spectrogram of a car horn looked like. So I did this for all of the wave files for the input data. This is a spectrogram of a siren, and this is a spectrogram of an air conditioner. So you can see that they're actually like fairly unique, even just from like a human like eye looking at it. So it should be suitable for us to train a network to recognize. So yeah, for this, we just reuse the same exact script, actually. I mean, it's a starting point. Obviously, there could be like differences in it, and so, but I think it's a good way to start an experiment. So we'll use the same amount of training steps, and we'll just give the image directory to be a different directory. This time, it's like the spectrograms directory. So for this one, yeah, I'm not going to train it like during the talk. It would be longer than the talk duration, but it took an hour to run on my MacBook, and it was 77.1% accurate on the test data. So that's actually still like quite accurate. The accuracy like depends on the type of problem that you're trying to solve. So if you want to get like a gauge of whether or not your model is doing well, then you should do a little bit of research on like that specific domain to know like how accurate models usually are. So yeah. Just like very quickly, so you like know like roughly what it looks like. We don't have so much time. This is TensorBoard, which was running in the background during both the trainings. And so yeah, it gives us the most useful thing is this accuracy graph. So accuracy 1 means like the accuracy of the top prediction in the probability distribution. So the top prediction that it produced was improving over time, like as we were training it. So these are the steps on the x-axis. We ran it for 500 steps. By the time we got to the end, we were at like the 77% accuracy. So yeah, roughly it would improve with the number of steps. There will be diminishing returns after a while, and it might actually be overfit if you do it for too much. So if you ran it for like 5,000 steps, you might start to see that it's no longer giving you any value. Okay, so if you're feeling overwhelmed by this, like that's totally normal, and it's an ever-evolving field. So I would just encourage you to experiment if it's something that your app like presents you with, like if it's a suitable thing to do, and also if you're just interested in it. I think it's like really fun, and I've been able to learn a lot of different like parts of this stack because of this, and also like refresh a lot of math knowledge, even though you don't actually have to go into the math if you don't want to. Yeah, so just like a wrap-up reminder. So this is not machine learning specific, but I think this is like a really nice like analogy. I saw this blog post recently by this woman, Devin Zweigel. I don't know if I pronounced her name right, but she basically was giving the argument that like a lot of what's important of being a software developer is to make sure that you are focusing like on the right parts of abstraction that you are like expected to, and to not be too overwhelmed by all the layers of abstraction that don't really have much to do with the tasks that you're doing and can just be like assumed to be okay. Yeah, so this, yeah, I think this is a really good parallel to machine learning because there's so much you could just spend like all your time like learning every little detail, but then you might not move forward if you go into all the rabbit holes. So where to find inspiration? Look at the open data sets, because that could like be a good starting point to tell you about problems that could be interesting to solve, that could match some of the apps that you work on. Read research papers. There are tons of them that come out. Like they vary in quality. I don't even know if I'm like a good person to judge the quality. I'm not an academic, but I found them to be like a lot easier to read like after I like got started. And you can even just read the abstracts, and then at the bottom they usually tell you just to get the gist of it, and then they'll tell you how to reproduce the results. So that's really cool because like people who have done their thesis on something like are experts on it, and then they leave you with like the data set usually and a GitHub repository to reproduce it. And then some blogs are very useful to follow. The Heartbeat blog, which I mentioned before, is about mobile-specific machine learning, and that's really nice blog. And then OpenAI is a company that does like research on like current machine learning problems, and they have a lot of good content, as well as they list content on machine learning problems that are still active areas of open research. So maybe these are ones that you avoid because they're maybe like problems that are too hard to solve right now. Yeah, so reproduce the results and do the same thing if you publish, like whether you publish a paper or you just like work on something in your app and then write a blog post. It's really nice if you like list all the details to reproduce it so that everybody can like work off of each other's previous work. And make sure you, like as with anything, make sure you check the licensing and attribute proper credit. And looking forward to the future, I think like the most notable things will be machine learning interpretability, which is basically explaining what machine learning model is doing at every layer of the network in more detail than like the visualization that I showed you, is a really exciting area right now. And Google just released a paper a month and a half ago on it, and we'll be able to like make more informed decisions with machine learning when we have this available. Also, Swift for TensorFlow is expected to be coming out in April, so any day now. And that will hopefully change a lot of things and simplify it for our stack. So yeah, this is a review of like what we went through. Is it practical for my app? What are the barriers to entry? They're perceived. What framework should be used? You can use any of them, but TensorFlow is what I recommend. And how do you navigate the material? I have some like resources for that. So yeah, I'll post these slides and probably even more resources because that's not exhaustive. And grazie. Thank you for having me.